All right, guys, go ahead and open up your notes. We're going to finish up 7.5 and 7.6 today. Reminder that your test is on Wednesday, and tomorrow we will review. We'll tie up some of the loose ends here, and hopefully the practice test that you did over the weekend has you prepared, or at least you're thinking in the right direction. Now, to that note, there were a couple questions on the practice test this weekend that pertain to what we're getting into today, in particular the Sierra Nevada mountains and then the fault block mountain, Horst Graben. So I will talk to you guys about that tomorrow, but when you see it in the notes today, hopefully it starts to click. All right? Now, what are the causes of mountain building? We've already talked about the idea that there are collision boundaries, which force continental crust into continental crust. They suture together, form big mountains. We also know that at subduction, you have the oceanic plate subducting underneath the continental plate, and therefore volcanoes are going to form on the overriding plate. We call those the volcanic mountain chains. So when you look through the next few slides, or as we go through the next few slides, I want you to pull back the information that you learned in plate tectonics, and hopefully it all ties it together. Now, as you're copying these, I want you to focus in on the idea that subduction is going to cause the oceanic plate under the continental plate, and the best example we have of that are the Andes Mountains. All right, so the whole west coast of South America has the plate subducting underneath, in particular the Nazca plate subducting underneath, creating a nice mountain range. So that should be a little bit of review. Now the next bullet underneath the subduction is the thrust fault. So if you remember, thrust faults formed by a compressional stress forcing the hanging wall above, right, pushing up and over the footwall. So think about forming a mountain where we're smashing things together, right, compressional stress, but rather than the ductile deformation that we get with folding, rather than one plate going underneath the other plate, which we get with subduction, here we're actually saying that we can push one block up and over the other. Great example of that would be the Palisades. So when you go over the George Washington Bridge, the whole Palisades over there, there's thrust faulting causing that whole cliff right there. All right. If you need these slides, if you missed something, this link will be up on my website for at least 24 hours. Now look here on the left, we have the Andes Mountains right over in here, and you can see we have the Pacific Ocean right up against. You have the Nazca plate going right underneath the North American plate, forming this whole range, and this is really where the Nazca plate is going to be sitting. What is that going to look like in terrain? Well, we're going to get some mountains, which you see on the right. But I want you to note, these mountains aren't like huge. They're not like super high mountains the way that we're going to see with the next set. Here we're looking at continental collision. Now, before you write a single thing, elbows, hands up, everybody, stop writing and listen to what I'm about to tell you. The major example that the textbooks always go to are the Himalayas because they're forming today. But the whole eastern seaboard of the United States, from Maine all the way down to Georgia, has been formed by collision boundaries. So when we had the Grenvillian orogeny, the Acadian orogeny, the Alleghanian orogeny, the Taconic orogeny, Taconic, like when you drive the Taconic Parkway upstate, these were all orogenies forming these huge mountains. So the way that we see the Himalayas today, the Taconic mountains were just as high in the past. But then weathering and erosion came in. And the weathering and erosion actually wore down those huge mountains and deposited them just to the west of the Taconic Mountains. And that's what we today call the Catskills. So I want you to be thinking, yes, Himalayas, great example. Everybody goes to it. It is going to be probably the go-to mountain range for a test. But the whole eastern seaboard, the Appalachian Mountains, the Taconic Mountains, all of those are the same continental collision. All right, and when they come together, when you do actually collide, this is where you're going to get a suture. Right, the idea that you're pulling blocks together. If you ever had stitches, they call those sutures. Right? Oh, I banged my head and I had to get 5 stitches. Well, those are sutures, but it sounds nicer to call them stitches, I guess. All right, go ahead and fill in these notes real quick. All right, for those that are done, maybe you're noticing the Alps there. Stop and think about where the Alps are. And now think back to Pangaea, right? When Europe, Africa, North America were all sandwiched together. It might help you to recreate the idea of this collision. Well, if we're forming much of North America, we were also forming much of Europe around the same time. So a lot of the mountains that go through Europe are also collision boundaries. We're also this continental collision mountain building effect. All right, again, if you need something, these notes will be up. And there, you got some nice pictures right there. You see the way that India is smashing into Asia, forming these huge mountains. We call them the Himalayas. And you see the picture on the right. You can tell that those are massively high mountains by the amount of snow that is collecting on them. All right, now, mountains form in response to continental rifting. This is just the opposite. We've been talking about compressional stress, smashing rocks together. But what happens if we actually start to pull the rocks apart? Tensional stress, stretching it out, it's going to cause some fault block mountains. So, back to that practice test that you got, the Sierra Nevada mountains are in fact fault block mountains. They're stretching, causing the blocks to fall down. And if I can doodle right across the bottom just for a second, you guys appease me, right? We're going to have lands that look like this. Up here we call these the horsts, Horst. And then down here, these are going to be called the grabens, Graben. And right here, and right here, you have normal fault. You see how the graben is the hanging wall? The hanging wall has dropped down in relation to the foot wall, right? So this is going to be a foot wall. This is also going to be a foot wall. Because as tensional stress pulls out this way and tensional stress pulls out that way, right, the crust actually starts to break apart in pieces, making this really unique landscape. So when we talk about basin and range, horsts and grabens, this is all fault block mountain. So I'll give you guys about another minute, because I'm sure the high-speed student right now has just sketched in what I sketched. That's a subtle suggestion. All right, not so subtle. Just another reminder, this is tension. This is not compression. Cool. So over here, hopefully you recognize that that's the west coast of the US. And this whole area right in here with the Sierra Nevadas is going to be fault block mountains, creating basin and range. And if we stretch things apart, well, this is going to create low-lying areas. And then we might have some high-lying areas over in here. All right, formation of rocks in and near mountains. Oh my goodness, look at all the words. At this time, I want you to open up in Schoology the last little set of notes. We're going to do some highlighting because this is a lot to write. All right, so I know it's going to take you guys a second to get them downloaded, but I want to point out that this particular slide, not a lot that you really needed to write anyway. It's really talking about the idea that sedimentary rocks can lead to the formation of some mountains. In particular, I mentioned that you could have your Catskill Mountains. Right, the Catskills are in New York. If you've ever been up like by Howe Caverns or Gilboa, New York, Cooperstown, all of those are mountains formed by sedimentary deposition. At one point in time, the whole west portion of New York State was actually ocean, and so there are actually a lot of fish fossils that you'll find up in those rocks, because as the mountains wore down, the sediment now collected in the ocean and basically preserved those marine fossils. On the right-hand side, we have igneous and metamorphic. So we know that as magma rises, right, it's going to push up onto the surface, making these volcanic mountain chains. We can also have plutons that make their way up, push up onto the surface. And then metamorphic rocks, we know regional metamorphism forming the whole northeast seaboard, right? From, again, Maine all the way down to Georgia, tons of metamorphic rocks. And your mountain building thrusts, which are circled in there, that's where we got our Palisades from. So it's good for you guys to read through these and again, build the connection between the three types of rocks, and then where do we actually go and see these rocks. Hopefully you've had enough time to download the notes. You can make some highlights. The other thing that we're talking about here is the idea of foliated metamorphic rocks. All right. So this one I really didn't need to give you, but it's going to save us a little time. So what causes the uplift and mountainous topography? So if you recall back in the last chapter with metamorphism, we said that rocks could be pushed down into the earth and then rise back up by this idea of isostatic rebound, right? And if you're like, wait, he didn't say that. I was talking about somebody on a pool raft. Somebody jumps on top of you. Now you sink down into the water. When that person gets off, you rise back up. Continents do the same thing to a limit, which we're going to see in the next slide. So as you suture them together, if the mountain's building up like this, well, then the root of the mountain is also going to build down like that. And then if I shave a little bit off here, well, then I'm also shaving a little bit off here. It's constantly going to balance itself out. It's constantly looking for what we call equilibrium. So this idea of balancing out is what we note with isostasy. So that's muy importante. Very important. All right, so how does this play out? Well, things change due to a variety of reasons. Pull out your little highlighter and highlight compressional stress, right? If we're talking about shortening and thickening, that's going to create compressional stress. That's what's going to then force the rocks down, right? Base goes down, and that's going to cause the bottom portion of that isostatic rebound. Now, as we add material on top, it's also going to force it down, right? So here, right, the weight of the lithospheric mantle pulls the lithosphere down, right? So as you're pushing them together, they're sinking further and further down. In the opposite direction, though, right? So in my head, I'm like, wait, this is a separate thought. If I have compressional, what if I have tensional over here? And remember, the tension is going to cause a thinning, creating a less dense, causing stretching. And now this is going to actually cause magma to rise up to the surface. So I've removed material. It's now become less pressure. Less pressure leads to melting. Melting causes, again, material to be less dense, and up to the surface it comes. So this is one of those things you guys got to take some time and really connect the dots with. Do I understand the stress? Do I understand what's happening at a particular plate boundary? And then what is the net result in forming a mountain? All right. And luckily for us, this is going to be the last slide for this chapter. All right, so uplift and erosion happen simultaneously. We open the chapter with that statement. We talked about the fact, right, we all picked our hands up and we pushed our fists together. Then we formed the mountain building, right? So then our hands went up together like a little mountain. And then we said, well, as they're building up, there's also erosion that's pulling them, right? Or not pulling them down, but actually like sanding them off. And so this is a constant cycle. But there's also another part to this, right? And this is where it gets a little crazy. If you think about Mount Everest is the highest mountain in the world, but it is limited on how high it can grow. because of this isostatic rebound, because it's floating on the asthenosphere, right, floating on the mantle. As the mountain grows higher, its root is also going to grow deeper into the earth. But there hits a certain point in depth where rocks are going to melt. So I want you to think about this. If I'm pushing it together and it has to balance itself out, but the bottom portion gets too far down and melts, well then more material can then be pushed down, right? There's this limit. And so as the mountain keeps trying to get higher and higher, the bottom keeps basically melting off, and you're not going to be able to get the mountain to grow any higher. So you hit a point, you can just keep melting as that root keeps going down. So you really can't grow any higher. It's a pretty cool concept. We'll review this again tomorrow, but just give it a little bit of thought, reflect on it. When you do the reading tonight on 7.5 and 7.6, when you write your 4 things that you've learned, which now are going to be based on what you learned from the reading, not just what you did in the notes, really try and reflect back on that. It's a neat process. So that wraps up the notes for today. I do want you guys to read through, really try and hone your understanding of these sections. We will not do 7.7 on the test on Wednesday, so you now have all the notes that you need. Go back to your practice tests, look that over. Maybe go and find other practice tests online and really prepare yourself for Wednesday. Make sure you know your vocab. And to my colleague who's covering my class, thank you so much for doing this. I hope you have a great day, all of you.